In this exercise, we have two relations defined on the set of people. We are tasked with determining whether these relations are reflexive, irreflexive, symmetric, antisymmetric, or transitive. So let's look at our first relation, is an ancestor of. So person A is related to person B if A is an ancestor of B. Now, is this relation reflexive? Well, it would be reflexive if every person was their own ancestor. This is, of course, not true. And in fact, this relation is irreflexive, since a person cannot be their own ancestor. Now, is this relation symmetric? So this would be symmetric if for every person A related to a person B, B is also related to A. But this can't be true, right? A person cannot be their own ancestor's ancestor. So, in fact, this is antisymmetric. And finally, is this relation transitive? Well, yes, the ancestor of an ancestor is an ancestor. Now, our second relation is married to. So person A is married to person B. Now, is this relation reflexive? No, a person cannot be married to themselves, so this is in fact irreflexive. Is this relation symmetric? Yes, right? If person A is married to person B, then person B is married to person A. So this relation is symmetric. And not antisymmetric. Finally, is this relation transitive? Well, if this relation was transitive, then that would mean by symmetry that a person is married to themselves. But this is, of course, not true. And there are the properties of these relations. In this exercise, we consider relations on the set of positive integers up to 4. Our task is to determine whether each of the relations is reflexive, symmetric, and transitive. Remember, a relation is reflexive if every element of the set is related to itself. The relation is symmetric if whenever x is related to y, then y is related to x. And a relation is transitive if whenever one element is related to a second and the second element is related to a third, the first element is related to the third. So let's take a look at the first relation. Now, in order to answer the question, it's useful to get a visual representation of the relation in question. So let's do that. In this diagram, pairs of elements that are related have an arrow joining the first of the pair to the second. From the diagram, we can easily see that this relation is reflexive. Every element in the set is related to itself. Furthermore, the relation is symmetric. For every arrow, there is an arrow in the opposite direction. And finally, the relation is transitive. Whenever we have one element related to a second and the second related to a third, the first is related to the third. So this relation is reflexive, symmetric, and transitive. Let's look at our second relation, and again we will draw the relation to help us answer this. Now, clearly this relation is not reflexive, since, for example, 1 is not related to itself. It is not symmetric, since, for example, 1 is related to 3, but 3 is not related to 1. And it is not transitive. For example, 2 is related to 3, and 3 is related to 4, but 2 is not related to 4. So the relation is not transitive. Let's draw our third relation. Now, looking at this diagram, we see that our third relation is not reflexive, since, for example, 2 is not related to itself. It is not symmetric, since, for example, 2 is related to 4, but 4 is not related to 2. But it is transitive. Now, there's no quick and easy way to prove this other than checking every case. But if you look through this diagram, you should be able to convince yourself that whenever we have one element related to a second and the second related to a third, the first element is related to the third. And this relation is transitive. Let's draw our final relation. This relation is not reflexive, since 3 is not related to itself. It is symmetric. Whenever we have an arrow, we have one in the opposite direction. But it is not transitive. For example, 3 is related to 2, and 2 is related to 4, but 3 is not related to 4. So our final relation is symmetric, but not reflexive and not. In this exercise, we consider 4 relations between pairs of integers. Our task is to determine whether each relation is reflexive, symmetric, and/or transitive. Remember, a relation is reflexive if every element, every integer in this case, is related to itself. It is symmetric if whenever x is related to y, y is related to x, and it is transitive if whenever x is related to y and y is related to z, we also have x related to z. Let's look at our first relation, in which x is related to y if and only if x is divisible by y. First of all, is this reflexive? Well, yeah, any integer is evenly divisible by itself. Any integer divided by itself gives 1. So this is reflexive. Is this relation symmetric? Well, 4 is divisible by 2, so 4 is related to 2 by this relation. But 2 is not divisible by 4, so 2 is not related to 4. So this tells us that the relation is not symmetric. If it were symmetric, then since 4 is related to 2, we would have 2 related to 4. This is not the case, so this relation is not symmetric. And is this relation transitive? Well, if x is evenly divisible by y, and y is evenly divisible by z, then x is divisible by z. So yeah, this is a transitive relation. Let's look at our second relation now. X is related to y if and only if x is not equal to y. First of all, is this reflexive? Clearly not. Any integer is equal to itself, so it is not related to itself by this relation. This is not a reflexive relation. Is this relation symmetric? Well, if x is not equal to y, then certainly y is not equal to x. So if x is related to y, then y is related to x. Yeah, this is a symmetric relation. And finally, is this a transitive relation? Well, 1 is related to 2, since 1 is not equal to 2. And 2 is related to 1, since 2 is not equal to 1. If this were a transitive relation, then that would tell us that 1 is related to 1. But that's clearly not the case. 1 is equal to 1, so 1 is not related to 1, and so this relation is not transitive. Relation B is not reflexive, it is symmetric, and it is not transitive. Okay, let's look at the third relation, in which x is related to y if and only if y is either 2 more than x or 2 less than x. Now clearly this is not a reflexive relation, since no number is 2 more or 2 less than itself. So this is not reflexive. Is it symmetric? Well, if x is related to y, then y is either 2 more or 2 less than x. If y is 2 more than x, then x is 2 less than y, which tells us that y is related to x. The other case, when y is 2 less than x, well, in this case, x is 2 more than y, which again tells us that y is related to x. So either way, if x is related to y, then y is related to x. So yes, this is a symmetric relation. Is this a transitive relation? Well, 2 is related to 4, since 4 is 2 more than 2. And 4 is related to 6, since 6 is 2 more than 4. If this were a transitive relation, then we would be able to conclude that 2 is related to 6, right? 2 is related to 4, and 4 is related to 6. So if it were transitive, then 2 would be related to 6. But 6 is neither 2 more nor 2 less than 2. So 2 is not related to 6, and this is not a transitive relation. Let's look at our final relation, in which x is related to y if and only if x is equal to y squared plus 1. First of all, is this relation reflexive? No. For example, 1 is not equal to 1 squared plus 1. Right? 1 squared plus 1 is 2. 1 is not equal to 2, so 1 is not related to itself. And that's enough to tell us that the relation is not reflexive. Is the relation symmetric? Well, 2 is related to 1, since 2 is equal to 1 squared plus 1. But 1 is not related to 2. 2 squared is 4, plus 1 is 5, which is not equal to 1. So 1 is not related to 2, so this is not symmetric. This is not a symmetric relation. Is this a transitive relation? Well, consider these pairs of elements. Two is related to 1, since 2 is equal to 1 squared plus 1. And 1 is related to 0, since 1 is equal to 0 squared plus 1. If this were a transitive relation, then we would be able to conclude that 2 is related to 0. But that is not the case. 0 squared plus 1 is 1, which is not equal to 2. So 2 is not related to 0. And so this relation is not transitive. Now, an equivalence relation is a relation which is reflexive, symmetric, and transitive. And none of these four relations satisfied that condition. None of them satisfied being reflexive, symmetric, and transitive. And so none of these are equivalence relations. In this exercise, we consider three relations defined over the set of positive integers. Our task is to determine which of these relations is reflexive, which are irreflexive, which are symmetric, which are antisymmetric, and which are transitive. Remember, a relation is reflexive if every element of the set, in this case the positive integers, is related to itself. It is irreflexive if no element of the set is related to itself. The relation is symmetric if whenever x is related to y, y is related to x. And the relation is antisymmetric if this is never the case, if no two different elements of the set are related to each other in both directions. And a relation is transitive if whenever x is related to y and y is related to z, x is related to z. Let's look at our first relation, which is the divisibility relation, where A is related to B if and only if A divides evenly into B. First of all, is this a reflexive relation? Well, any positive integer evenly divides into itself. Right? Any positive integer divided by itself gives 1. And so this is a reflexive relation. Every positive integer is related to itself. So this is reflexive, and it is not irreflexive, since it is not the case that no element is related to itself. Is this a symmetric relation? Well, 2 is related to 4, since 2 divides evenly into 4, but 4 does not evenly divide into 2, so 4 is not related to 2. So this is not a symmetric relation. In fact, it is antisymmetric. If we take any two different positive integers, x and y, say, if x divides evenly into y, then y cannot evenly divide into x. So they can be related in at most one direction, and so this is an antisymmetric relation. Is it a transitive relation? Well, if x divides evenly into y and y divides evenly into z, then certainly x divides evenly into z. So yeah, this is a transitive relation. Next, let's look at the relation in B, the relatively prime relation, where A is related to B if and only if their greatest common divisor is 1. So first of all, is this a reflexive relation? Consider the integer 2. The greatest common divisor of 2 and 2 is 2, not 1. And so 2 is not related to itself. And so this relation is not reflexive, since it is not true that every element is related to itself. Is this relation irreflexive? Is it the case that no element is related to itself? Well, no, that's not true either. The greatest common divisor of 1 and 1 is 1. So 1 is related to itself. So the relatively prime relation is neither reflexive nor irreflexive. Is it a symmetric relation? Well, if the greatest common divisor of A and B is 1, then certainly the greatest common divisor of B and A is 1. So if A is related to B, then B is related to A. And this is a symmetric relation. And it is not an anti-symmetric relation, since what I just said also holds for different positive integers A and B. So it is symmetric and not anti-symmetric. Is it a transitive relation? Well, 2 is related to 3, and 3 is related to 10. 2 and 3 are relatively prime, and 3 and 10 are relatively prime. Now, if this were a transitive relation, then we would be able to conclude that 2 is related to 10. But in fact, the greatest common divisor of 2 and 10 is 2, not 1. They are not relatively prime. 2 is not related to 10. And so this relation is not transitive. Let's look at our third and final relation. This is the relation which holds between A and B if and only if A and B differ by a multiple of 3. So, first of all, is this relation reflexive? Well, the difference between a positive integer and itself is 0, which is a multiple of 3. And so any positive integer is related to itself, and this relation is reflexive. And so it is not irreflexive, since it is not the case that no element is related to itself. So this is reflexive and not irreflexive. Is this relation symmetric? Well, if A and B differ by a multiple of 3, then of course B and A differ by a multiple of 3. So yeah, this is symmetric and not anti-symmetric. And finally, is this relation transitive? Well, if A is related to B, then A and B differ by a multiple of 3. And there's another way we can write that. So if A is related to B, then A is equal to B plus 3 times J, where J is an integer. It may be positive or negative, or 0. Now if B is related to C, then we can write a similar equation with B and C. Okay, so if A is related to B and B is related to C, then these two equations hold. But now we can substitute this for B in our first equation, and rearrange the right-hand side a little bit. And we get this. A is equal to C plus some multiple of 3. Right? Since J and K are both integers, their sum will be an integer. And so this is C plus a multiple of 3. So A and C differ by a multiple of 3. So A is related to C. And so this relation is transitive. If A is related to B and B is related to C, then A is related to C. In this exercise, we have 6 relations defined on the set of real numbers. Our task is to determine whether each is reflexive, symmetric, or transitive. Let's start with relation A, where x is related to y if and only if x minus y is rational. So, is this relation reflexive? Well, for any real number x, x minus x is 0, which is rational. So yes, this is reflexive. Is this symmetric? Well, if x minus y is rational, then y minus x is rational, right? Say x minus y is a rational number r, well then y minus x is just minus r, which is rational. And is this relation transitive? Well, if x is related to y and y is related to z, that is, x minus y is rational and y minus z is rational, well, adding these together will give us a rational number. And you see that the y's cancel to give us x minus z. So yes, x is related to z, and so this relation is transitive. Let's look at relation B, where x is related to y if and only if x is 2y. So x is y doubled. Well, is this relation reflexive? Well, no. For example, 1 is not related to itself, right? So this is not a reflexive relation. Is this relation symmetric? Again, no it isn't. 1 is related to a half, but a half is not related to 1, right? 1 is 2 times a half, but a half is not 2 times 1. So, no, this is not symmetric. Now, is this relation transitive? Well, 4 is related to 2, and 2 is related to 1. But 4 is not related to 1, right? 4 is not 2 times 1. So no, this relation is not transitive. Let's look at relation C. X is related to y if and only if x times y is non-negative, right? So, is this relation reflexive? Well, yes. If you take any real number and square it, the result will be non-negative. So yes, this is reflexive. Is this relation symmetric? Well, x times y is the same as y times x. So if x is related to y, then of course y is related to x. And is this relation transitive? Well, consider this case. Let x be 1, let y be 0, and let z be minus 1. Well then, x times y gives 0, so x is related to y, and y times z gives 0, so y is related to z. But x times z is 1 times minus 1, which is minus 1, and so x is not related to z. So this shows that the relation is not transitive. Now let's look at relation D. X is related to y if and only if x times y equals 0. Is this relation reflexive? No, right? 1 is not related to itself, for example, since 1 squared is not 0. Is this relation symmetric? Well, yeah. Again, x times y is the same as y times x, so if x is related to y, then of course y is related to x. And is this relation transitive? Well, no. Using similar reasoning to the previous relation, if we take x to be 1, y to be 0, and z to be 1, then x is related to y, since x times y is 0, and y is related to z, since y times z is 0, but x is not related to z, since x times z is 1. So this is not transitive. Okay, relation E. X is related to y if and only if x equals 1. Is this relation reflexive? Well, 2 is not related to itself, right? Since 2 is not equal to 1. So, no, this relation is not reflexive. Is this relation symmetric? Well, if we take x to be 1 and y to be 2, 1 is related to 2, but 2 is not related to 1, right? Since 2 is not equal to 1. So, this is not symmetric. And finally, is this relation transitive? Well, if x is related to y, then x equals 1. And if y is related to z, then z equals 1. And so x, of course, is related to z, since x is still equal to 1. So, yes, this is a transitive relation. Let's look at our final relation, relation F. X is related to y if and only if x equals 1 or y equals 1. Okay. So is this relation reflexive? Again, no, it's not. 2 is not related to itself. It's not reflexive. Is this relation symmetric? Yes. Well, if x is related to y, then either x is 1 or y is 1. So flipping them around won't change that fact. And y will be related to x. Yes, this is symmetric. And finally, is this transitive? Well, consider x equals 2, y equals 1, and z equals 2. Then x is related to y, since y equals 1, and y is related to z, since y equals 1 again. But x is not related to z, since they are both 2. So this is not transitive. In this exercise, we consider 4 relations defined on the set of books. Our task is to determine if each relation is reflexive, symmetric, or transitive. Let's start with the relation in A. A is related to B if and only if the cost of A is greater than or equal to the cost of B, and the length of A is less than or equal to the length of B. Now this relation is reflexive, right? The cost of a book A is greater than or equal to itself, the cost of itself, it is equal to, right? And the length of a book A is equal to itself, so it is less than or equal to itself. So A is related to A. Is this relation symmetric? Well, if A is related to B, then the cost of A is greater than or equal to the cost of B. And so it is not necessarily the case that the cost of B is greater than or equal to the cost of A. In fact, the only time when this is the case is when they are equal. So generally, if A is related to B, then B is not necessarily related to A. So this relation is not symmetric. Is this relation transitive? Well, if A is related to B and B is related to C, then the cost of A is greater than or equal to the cost of B, and the cost of B is greater than or equal to the cost of C. So certainly the cost of A is greater than or equal to the cost of C. And the length of A is less than or equal to the length of B. And the length of B is less than or equal to the length of C. So certainly the length of A is less than or equal to the length of C. So yes, A is related to C, so this relation is transitive. If A is related to B and B is related to C, then A is related to C. Let's look at B. A is related to B if and only if the cost of A is greater than or equal to the cost of B, or the length of A is less than or equal to the length of B. First of all, is this a reflexive relation? Well, yes. The cost of a book is equal to itself, so this condition holds. So it is reflexive. Is this a symmetric relation? Well, if book A costs more than book B, then A is related to B, but it's not necessarily the case that B is related to A. It's possible, but it's not necessarily the case. So no, this is not a symmetric relation. Is it a transitive relation? Well, if book A costs more than book B, and book B is shorter than book C, then A is related to B and B is related to C. But it's not necessarily the case that A is related to C. C may cost more than A, and A may be longer than C. So no, this is not a transitive relation. Let's look at C now. A is related to B if and only if A and B cost the same and they have the same number of pages. Again, this is a reflexive relation. Of course, a book costs the same as itself and it has the same number of pages as itself. So this is reflexive. Is it symmetric? Well, if A costs the same as B, then B costs the same as A. And if A has the same number of pages as B, then B has the same number of pages as A. So yes, this is symmetric. And finally, is it transitive? Well, if A is related to B and B is related to C, then A and B cost the same and B and C cost the same. So certainly A and C cost the same. And if A and B have the same number of pages and B and C have the same number of pages, then certainly A and C have the same number of pages. So yeah, in that case, A and C are related. A is related to C. So this is a transitive relation. And in fact, this is an equivalence relation, since it's symmetric, reflexive, and transitive. Now, D next. A is related to B if and only if A and B cost the same, or A and B have the same number of pages. Again, this is a reflexive relation. Any book costs the same as itself, so it satisfies the first condition, and so it's related to itself. Is this relation symmetric? Well, if A is related to B, then either A and B cost the same, or they have the same number of pages. In either case, B is then related to A. So yeah, this is symmetric. Is it transitive? Well, if A and B cost the same, then they are related. And if B and C have the same number of pages, then B is related to C. But then it's not necessarily the case that A is related to C. A and C may not cost the same, and they may not have the same number of pages. So they might not necessarily be related, and so this is not a transitive relation. So this relation is reflexive and symmetric, but not transitive. And we're done. In this exercise, we have defined a relation R on the set A of positive integers less than 30. Now, x is related to y by R if and only if x and y have the same prime factors. So, for example, 12 is related to 18 by R, since 12 is 2 times 2 times 3, and 18 is 2 times 3 times 3, so both have prime factors 2 and 3. Now, clearly a number has the same prime factors as itself, so R is reflexive, and if x has the same prime factors as y, then y has the same prime factors as x. So R is symmetric, and if x has the same prime factors as y, and y has the same prime factors as z, then x and z must have the same prime factors. So R is transitive. So R is reflexive, symmetric, and transitive. So this means exactly that R is an equivalence relation. Now, since R is an equivalence relation, we know that we can partition the set A into equivalence classes, right? Now, our task is to do exactly this, to write out all of the equivalence classes of the relation R on the set A. So, let's start by writing out the elements of A. Now let's find our equivalence classes. 1 has no prime factors, and this is not the case for any other of these numbers. So the equivalence class of 1 consists of just itself. Right, now 2 has prime factor just 2. And this is also true for 4, 8, 16, right? Note that these are just the powers of 2, right? Now 3, again, has just prime factor 3. And this is also true for the powers of 3. So 3, 9, and 27. Now we get to 4, but 4 is already in the equivalence class of 2. So we know that the equivalence class of 4 is just identical to the equivalence of class of 2, so we don't need to write this out. So we'll move on to 5. Now 5 has prime factor 5 and nothing else, and this is also true for 25. Now 6 has prime factors 2 and 3. Which other numbers have prime factors 2 and 3? Well, as we noted earlier, 12 is 2 times 2 times 3, and 18 is 2 times 3 times 3, and our fourth and final element of this equivalence class is 24, given by 2 times 2 times 2 times 3. Now, the next element we come to is 7. Now 7 has prime factor just 7, and no other number in this range has prime factor just 7. So the equivalence class consists of just 7. Now 8 is already in the equivalence class of 2, and 9 is already in the equivalence class of 3. So we move on to 10. Now 10 has prime factors 2 and 5. Now this is also true for 20. Now the equivalence classes of 11 and 13 consist of just 11 and 13 respectively. And the next element we look at is 14, which has prime factors 2 and 7. 28 also has prime factors 2 and 7. Now we note that all of the remaining numbers are too large for 2 to be in the same equivalence class. So the remaining numbers must each have their own equivalence class consisting of just themselves. Now we have completed our list and we see that R partitions the set A into 18 distinct equivalence classes. Consider this relation R defined on the set of positive integers less than 30, where x is related to y by R if and only if x and y share a common prime factor. Is R an equivalence relation? Remember, a relation is an equivalence relation if it is reflexive, symmetric, and transitive. Now clearly R is symmetric. If x is related to y, then y is related to x. But R is not a reflexive relation, since 1 is not related to itself. This is because 1 doesn't have any prime factors, so it does not share a common prime factor with itself. Furthermore, R is not a transitive relation. For example, 6 is related to 15 since they share the common prime factor 3. And 15 is related to 25 since they share the common prime factor 5. However, 6 is not related to 25. The prime factors of 6 are 2 and 3. The prime factor of 25 is just 5. So 6 is not related to 25, which tells us that this relation is not transitive. The relation is not reflexive and not transitive, and so in this exercise, we have a few questions to answer. Firstly, we want to know what is the finest partition of a set A. What we mean by this is that it cannot be refined into a different partition. So we know that given a set A, we can partition it into a certain number of groups, right? And now we can refine this partition by splitting each of these groups into smaller groups, right? And we're asking for the partition that cannot be refined further, right? So that all of the groups in this partition cannot be split into smaller sets, okay? So for this to be true, it must be the case that each of these groups consists of just one element, right? So the finest partition consists of exactly the singleton sets of all elements in A. Now, what equivalence relation does this define on the set A? So suppose that this partition is the set of equivalence classes of this relation, right? What relation is this exactly? Now, two elements are related if they are in the same equivalence class, right? But in this case, each equivalence class consists of just one element. So an element in A is related only to itself by the equivalence relation defined by this partition. Okay? And this is exactly the identity relation on A. Next, we want to know what is the coarsest partition of the set A. Coarsest simply meaning least fine, right? So what is the least fine partition? Now for the finest partition, we want to find a partition into groups such that the groups can no longer be split up, be refined, right? This is the opposite, so we want everything to be together in the same group in this partition, right? So in other words, this partition consists of just one set, the set A itself. Now what is the equivalence relation defined by this partition? Again, remember that two elements will be related by this relation if they are in the same equivalence class, and in this case there is just one equivalence class containing every element of A, right? The equivalence class is A. So any pair of elements in A will be related by this equivalence. So this defines the universal equivalence. The universal relation relates any two elements of A. Consider this binary relation on the set of pairs of positive integers, where the pair AB is related to the pair CD if and only if AD equals BC. Now, is this relation an equivalence relation? In other words, is it reflexive, symmetric, and transitive? Let's check those three properties, beginning with reflexive. Now, is it true that any pair is related to itself? But yeah, clearly it is, since A times B is equal to B times A. Now let's check the symmetric property. So we need to check whether this statement is true. If AB is related to CD, then CD is related to AB. But what do these mean? Well, if AB is related to CD, this means that AD equals BC. And by rearranging this, we can clearly see that, yes, CB equals DA, which is what is required for CD to be related to AB. So the symmetric property holds. Finally, let's check the transitive property. So we need to check whether this property is true for this relation. If AB is related to CD and CD is related to EF, then AB is related to EF. Right. So let's first write down what these three mean exactly. We need to check that if these two statements are true, then this statement can be logically deduced. So Let's start by writing down AF. Now let's multiply and divide by D. Now we can substitute BC for AD. And then CF equals DE. And finally, we can cancel the D's again. And there is our confirmation. Given these two, we can find that this is true. And so this is a transitive relation.